Hello there, this is Physics Chapter 11, Lecture 1. You're going to need to open your book to page 351. Actually, 352 is the first page we'll be looking at. And have a printout, a blank printout of your Chapter 11 lecture notes. So this chapter is about waves. We'll be concentrating on sound waves and light waves. I left you some space. So a wave is a disturbance that propagates a medium, all right? It propagates is a fancy word for moves. A medium could be air, could be water, could be a solid, right? But the first thing we'll talk about is the kind of wave that you probably looked at in chemistry class, and that is a transverse wave. That's like a wave in the ocean. And so take a second, go ahead and pause the video and take a second and draw this out in your blank space. All right, so the height of the wave we call the amplitude. The distance from crest to crest, or trough to trough, is called the wavelength. We use the Greek letter lambda for that. Crest is the top part of the wave, the highest point of the wave, and then the trough is the lowest point on a wave. Now we have an equation for frequency. It's velocity over wavelength. All right, you're going to need to memorize that. You'll use that a lot and put it in the blank space on your notes. The next thing on your notes, and by the way, I put delta. I believe that Greek symbol is actually lambda there, so you can correct me. I need to brush up on my Greek symbols there, but I believe it's lambda. A longitudinal wave is a wave in which propagation is parallel to oscillation. You want to think of that as a slinky, kind of. And we have a picture, a drawing of the longitudinal wave on page 353. The points of high pressure are called compressions. So you can almost think of those as like a crest on a wave. And the areas between pulses or areas of high pressure are called rarefactions. All right, so longitudinal waves describe sound waves, while transverse waves describe light waves. All right, so on to sound. Now, for this chapter, I will have a lot of videos linked in the description box. You should watch those videos. It really helps to describe what's going on. Okay, so that'll really help you and save you a lot of time of trying to figure out all of this stuff. Just a picture, in this case, a video is worth 1,000 words. So sound is the medium. The medium for sound typically is air. All right, air is pushed outward from the source, clumping it together to form a compression. All right, compression on a longitudinal wave. Rarefactions form as the source ceases. So on page 354, we have a diagram on how the ear works, and you do need to know the basics of this diagram. All right, the external auditory meatus, the auditory ossicles, tympanic membrane, the cochlea. You need to know what all those parts of the ear do. You need to know the path from the ear canal or the external auditory meatus to the spiral organ. Now I'm going to link a video there for you to watch. In terms of what you hear, we use the term pitch. And that's an indication of how high or low a sound is. So higher frequency means a higher pitch. Smaller wavelength would give you a higher frequency, also a higher pitch. Volume isn't determined by frequency. Volume is determined by amplitude. The larger the amplitude, the further in and out your eardrum will oscillate, and that increases volume. All right, so a lot of vocab. Again, watch the videos. So now we're going to get into a little bit of the math. And you need to know the speed of sound equation in air. All right, so that equation is volume is equal to 331.5 plus 0.606 T. And that is the temperature in degrees Celsius. All right, so the warmer the air, faster air travels. Let's look at, on your own, 11.1. So this is on page 358. All right, let me bring that into view. So it says, what is the frequency of a sound wave whose wavelength is 1 meter? Assume that the air has a temperature of 15 degrees Celsius. Is the pitch higher or lower than 440 hertz? All right, so we know that our wavelength is equal to 1 meter. Temperature is equal to 15 degrees Celsius. So first we can figure out the velocity. That's 331.5 plus 0.606 times the temperature, 15. That's 340.59 meters per second. That velocity allows us to figure out the frequency. Frequency is going to be the velocity over the wavelength, 340.59 divided by 1 meter. All right, hopefully you don't need your calculator for that. That's 340.59 and the, not meters per second, and that is going to be hertz. The unit for frequency is hertz, and that's lower than 440 hertz, so it will have a lower pitch than the standard A. All right, I think I can fit 11.2 into this space here. So 11.2 says, if a sound wave of frequency 501 hertz has a wavelength of 0.697 meters, what is the temperature of the air through which the wave is traveling? All right, so on this one, we know that the frequency is equal to 501 hertz. We know that the wavelength is 0.697 meters. So we can get the velocity. All right, velocity, if we rearrange this equation, it's frequency times wavelength. So that's going to be 501 hertz times 0.697 meters. All right, so we would get a velocity of 349.2 meters per second. We can now plug that velocity into this equation that involves temperature. So we'd have 349.2 is equal to 331.5 plus 0.606 T. So solving for temperature, that's going to be 349.2 minus 331.5 divided by 0.606. All right, and you will get 29.2 degrees C. That'd be a nice warm summer day. All right, so pause the video if you're still writing, and I will erase this and move on. Okay, our next topic is the Doppler effect. So we have an illustration on page 359 in the book. Definitely worth looking over, figure 11.5. I'm going to link a couple of videos about the Doppler effect, short videos that really worth your time to watch. But the Doppler effect is a change in pitch caused by relative motion between the sound and the source or the observer. Okay, so when you think of the Doppler effect, I think of, so if you have a car that goes past you or a train that goes past you, it's honking its horn, you hear as it moves past you the lowering of the pitch of the sound. So I've got a little space for the Doppler effect equation, and that is the frequency observed. All right, frequency observed is equal to the velocity of sound plus or minus the velocity of the observer, and I'm going to write these words out fully this time, but not from now on, over the velocity of sound plus or minus the velocity of the source times the true frequency. So that'd be the frequency. The true frequency is just the frequency if the source weren't moving, or there was no movement by the source or the observer. Now, how do I remember this equation? I think of it alphabetically. You've got the velocity of sound over the velocity of sound. That's pretty easy to remember. Observer in the alphabet, O comes before S. So observer goes on top, source goes on the bottom. Now, whether you use a plus or minus, I'm going to explain that to you as we work the problem. So let's look at 11.3. And we are on page 363. Okay, so it says a man has just said goodbye to his friend who's boarded a train. He stands and watches the train as it travels away from the station at 35 meters a second. If the train blows its horn with a frequency of 411 hertz when the train is stationary, that's the true frequency. What's the frequency that the man will hear? What's the observed frequency? And we have a temperature of 25 degrees C. So first of all, we have to figure out the velocity of sound. All right, and we're going to use our velocity of sound in air equation, 331.5 plus 0.606 times 25 degrees Celsius. That is 346.65 meters per second. And we want to know what is the observed frequency, all right, of the train. Okay, so first of all, we know it's velocity of sound over velocity of sound. So I'm going to dispense with putting the units. It makes everything a bit too messy. 346.65 over 346.65. All right, now the train is moving. The train is the source. The observer is just standing there. So if the observer is just standing there, it's just going to be a 0. All right, we also know the true frequency is 411 hertz. So I can go ahead and put that there. So the tricky part, the velocity of the train, we also know is 35. So let's put that in. The tricky part is, do we put a plus or a minus here? Well, the train is moving away from the source. Moving away from the source. That means the pitch will go down. All right, the frequency will go down. So this fraction, in order to make it to be, the answer we know is going to be less than 411 since the train is moving away. So I'm going to need to put a plus here so that this entire fraction will be less than 1. All right, that's how you figure it out. You just use logic. So our frequency observed is going to be 346.65, because it's plus 0. 346.65 plus 35. All right. Tell you what I'm going to do. Let's go ahead instead of writing all that out again. Sorry about that. Take a second to erase. I'm just going to write 346.65 over 346.65 plus 35. That gives you 0.908. All right, that's what that turns out to be. There's no reason to write it all again. And then times 411. So we get an observed frequency of 373.3 hertz. All right. Let's see if I can fit in 11.4 here. So we're still on page 363. And it says a woman is driving toward a factory to pick her husband up after work. As she travels toward the factory starts to blow the whistle, indicating the end of the workday. If the whistle's frequency is 494 hertz and the woman hears that at 511, how fast is the woman driving? All right, so we're working with this. Now, that's again at 25 degrees C. So we know that the velocity of sound, because we figured this out in the previous problem, it's 346.65. Okay, so she observes the frequency at 511. Okay, so we know we're going to have 346.65 over 346.65. Now the factory is the source, the factory whistle. Is the factory moving? No, the factory is not moving. So the bottom is going to be 0. So I just got to figure out velocity. All right, the observer is moving. I got to figure out, is that a plus or a minus? We also know that the true frequency is 494. All right, so in order to get a fraction that is greater than 1, because I know I'm going to multiply that fraction by 494 to get a bigger number, 511, then we're going to have a plus here. Okay, so the way that I would do this algebraically is I bring that 494 underneath the 511. So we have 511 over 494 is equal to 346.65 plus V over 346.65. All right, that 511 over 494 is 1.03. You can take that out more decimal places if you want, but 1.043. I'm going to multiply that by the denominator, 346.65. All right, so that is just 1.03. We're going to multiply both sides by 346.65. That equals 346.65 plus V. All right, so if we solve for V, multiply those two together, then subtract 346.65, you'll get the velocity is equal to 11.9 meters per second. All right, so give that a try. That's the way I prefer to do the algebra. You could multiply 494 by the tops there and then do all that, and you're going to come up with the same answer as long as you have the same rounding. Okay, let's move on. We'll finish this lecture up in just a second. And we'll do the bottom half now of page 3 on your notes. So sound waves and other substances. So if you will look at table 11.1 on page 363, you'll see the speed of sound in air is 343 meters a second, and it gives a bunch of other substances. And notice that air is the slowest one. Methyl alcohol, that's a liquid, 1143 meters per second. Water, 1493. And then it's got some solids. Aluminum, 5100 meters per second. So you can see that sound travels different speeds in different substances. So the harder a medium is to compress, the faster sound travels. It's usually fastest in solids. Slowest, mark that out, slowest in gases. I'm not sure if your lecture notes still have liquids. I may have fixed that over the years, but it should be gases. And why is that the case? Well, the less elastic the medium, the less disturbance occurs and the faster the waves move. Now here's these next few bullets. Sonic waves are the normal range of human hearing, 20 to 20,000 hertz. All right, most of us can't hear all the way up to 20,000 hertz because of just ear damage over the years, but a newborn might be able to. Ultrasonic waves, greater than 20,000 hertz, that would be like an ultrasound machine, uses those kind of sonic waves. And infrasonic waves, less than 20 hertz. All right, and I will be posting a video about how an ultrasound imager works. Let's finish up this lecture. Let's look at page 367. We'll do 11.5 and 11.6. So 11.5 says, if you hear thunder 2.5 seconds away after seeing a lightning flash, how far away was the lightning formed? And assume a temperature of 20 degrees C. So 11.5 on page 367. So first of all, we need to get, we're going to use the equation distance equals rate times time. We need to get the rate or the velocity. That's 331.5 plus 0.606 times 20. And if you plug that into the old calculator, you get 343.6 meters per second. All right, so our distance, okay, and we're wanting to know how far away, so we want to know the distance. Distance is going to be the velocity or the rate, 343.6 times the time. The time in the problem is 2.5 seconds. So this is your basic velocity equation from chapter 1. All right, and that's going to be 859.05 meters. Of course, we use delta x, all right, but I'm kind of putting some pre-cal into this lecture because it's so easy to remember that distance equals rate times time equation. And 11.6. Suppose you're watching the start of a race. The official raises his starter's pistol into the air and fires. You see a cloud of smoke rising from the pistol, indicating that it is fired, but you do not hear the sound of the pistol right away. If you're 402 meters away from the starter and the temperature is 25 degrees C, how long will it take you to hear the sound? All right, we're going to start with our distance equals rate times time equation again. We want to know the time. Distance over rate. We know the distance. Let's get the rate. We know velocity or the rate is 331.5 plus 0.606 times 25. So that is going to be 346.65. And then time will be the distance, 402 meters, divided by the rate, 346.65 meters per second. So that gives us just a little over 1 second, 1.16 seconds. So you see the smoke from the pistol, but it takes a little time for the sound to get to you because sound travels a lot faster than light. So the homework from this section, from this lecture, review questions, page 383. Go ahead and do 1 through 4. Practice problems, page 384. You can do 1 through 6. That does it for this lecture. We will finish up chapter 11 next lecture, talking about light.